Okay, so in this video, I'm going to talk about vertical and horizontal dilations. So suppose C is positive, real number, and say we have a function that is a parent function, and then we multiply that function by this constant. So let's say I call this g of x. G of x equals c times x, where f of x is a parent function. F of x is a parent function. So then if the c is bigger than 1, so we will have like two cases here. So the graph will be expanded vertically. So the graph of f of x is expanded vertically. So f of x expanded vertically. C is bigger than 1. And otherwise, the graph of f of x is compressed vertically. If c is between 0 and 1. So I can illustrate this like this. Let's say you have, this is the parent function f of x, y equal f of x. Right? If c is bigger than 1, then it will expand it. It will expand it vertically like this. So this red one is the graph of g, basically. C is bigger than 1. So this is the case when c is bigger than 1. So basically every point here is moved up. So to write the formulation for this, I can say this because here the y values are multiplied by c. So any point xy will be dilated. So I'm multiplying the y values by c. So it will be x times cy. So that's why the graph sort of moves up by a factor of c in vertical direction. Okay, so that's case 1. Now for case 2, suppose, so let me do that on the next page. So this is a formulation for this case. Now for the next case, an example could be this. So say you have f of x, again, a parent function like this. Then the gx will be wider. But you see, it moves down, so the points are moving down. So if you pick a point here, for instance, this point moved down by a vertical dilation, okay? Because c is between 0 and 1 in this case. And the formulation for this one will be like, if you pick a point here and call that point xy, then this will be translated as x times c times 1. And this c is between 0 and 1. That's why the y values get smaller. And if they get smaller, then the graph will be compressed vertically, right, in y direction. Okay, so that's that. Now, for the horizontal case will really just be opposite of this. But let me write down the exact statement. So again, we're supposing that we have a positive number c, then the function g, which is obtained by dilating the function f, and this time we will multiply the x values by c. So the first case, when it's vertical, we're multiplying the y values by c. In this case, we're multiplying x by c. So again, you will have two cases, but those cases will be completely opposite of the vertical case. So the function f of x is compressed. F of x is compressed, but c is bigger than 1. So remember, in the vertical case, this was expansion, right? So now it's compression. So the second case, f of x is expanded if c is between 0 and 1. If c is between 0 and 1. So here is an example. So let's say this is some parent function f of x. This is f of x. Now the first case, we're calling it compression in horizontal direction. So that means this is going to get smaller. This gap is going to get smaller. So it will be like this exactly. This is when c is bigger than 1. Okay. And then the other case, again, let's say you have a parent function like this. And then this will now horizontally expand it this way. So it's going to expand it like that horizontally, right? In x direction, basically. So this is the case when c is between 0 and 1. So let me just give you guys an example. Let's say you take this. So here is an example. You take this. So let's say u of x equals 1/4 x cubed. So now we'll look at this one. See the y, this is a y value, right? This is the parent function, and the y value is multiplied by 1/4. So basically this is your c, right? And this is between 0 and 1. If it's between 0 and 1, then we're talking about the vertical dilation here. So it's a compression vertically. So then the x cubed, the graph of x cubed is like this. This is a graph of x cubed. Graph of x cubed is like that. This is the parent function. Now, if this is going to be a dilation, then the y value should get smaller, right? So then it should be below like this. It should be like that. This will be y equal to, or g equal to rather, gx equal to 1/4. Now, if I just kind of create a small table here, I can show you, because remember, xy is going to be translated onto x1/4y. So if I just pick a random point on x cubed, so let's say I choose x to be 2, and this will be 8, right? Because 2 cubed is 8. Now this point will be translated onto x is 2. Now multiplying by 4, so that will be 2, 2. Okay, so if this point was somewhere right here, for instance, 2, 8 is somewhere right here, now it becomes 2, 2, so it went all the way down here. I hope that makes sense. Now let me just give you another example. Let's say I have this function. So y equal to, let's say, absolute value of 2 times x. Well, absolute value of x, so this is, this is really just this. You can write this as, so if I pick a point, let's say I just pick a point on the parent function, because remember we said that, you can pick, let's say, if x is 1, then the y value will be 2. 1, sorry, if I pick it on a parent function. So this is 1, 1. And then if you plug it into this function, then it will be 1, 2. And now this is the absolute value function, and 1, 1 is right here. And now I have 1, 2. So where is 1, 2? 1, 2 moved up this way. So therefore, the graph is going to look like this. Like this. Okay, so you can call this, see, if you look at it horizontally, then the graph moves this way. So you can call this compression, right? You can call it a horizontal compression. So it could be horizontal compression. And this was the opposite of expansion, vertical expansion, or you can say vertical expansion. So these two are completely opposite of each other. So you can call either one of them. Okay. So I hope this makes sense.